G'day, I'm James, and welcome to the beauty and the thinking behind matrices and transformations. So we've been talking about matrices in a previous video, and today I want to talk about matrices with a geometric application, how they transform points in the plane, how they move things around. That's what I mean by transformation, moving points around on a plane and get some sort of geometric motion of some kind. For example, here's some points in the plane. It's the plane of the piece of paper. And I've got a dot pointing this way right now. If I give this piece of paper a 90-degree rotation in the counterclockwise direction, all the points move like that. Though I suppose the very center point didn't actually move. All right, that's one 90-degree rotation. Let me give it a second 90-degree rotation. Same direction, counterclockwise, zoom. So there's the net effect of two 90-degree rotations on this piece of paper. It went zoom, zoom. In fact, you can see, really, those two rotations together combined to make a single 180-degree rotation. Two rotations in the plane gave me another rotation overall. Okay, so here's my puzzle. I'm wondering if the same thing is true in 3 dimensions. For example, here's my arm. Hopefully you can see my arm. Probably looks funny because my hand's probably really close to the camera. All right, I'm going to give my arm a 90-degree rotation about this axis. Zoom. See what I did then? Now I'm going to give my arm a 90-degree rotation about this axis. Zoom. So there's the combined effect of two 90-degree rotations in 3-dimensional space. Look, I started this way with my palm up, zoom, zoom, and I end this way with my palm facing my chest. So my question is, starting there and ending there, is that itself a rotation? Now, I'm afraid it's not a 90-degree rotation, because if I did a 90-degree rotation, zoom like that, my palm is facing upwards. Instead, I need to end with my palm facing my chest. So it's not a simple 90-degree rotation this way. So there is my puzzle. Does doing this motion, followed by that motion, have the same effect as doing a rotation somehow? Now, I twisted my hand there, so something weird's going on. Is that a rotation in 3-dimensional space? Do two rotations in 3-dimensional space make another rotation? That's the mystery. In 2 dimensions, it seems to be true. A rotation followed by a rotation seems to be a rotation, but now it's more mysterious in 3 dimensions. All right. However, today we will stick with 2-dimensional motions because we have a complete theory of matrices in 2 dimensions, 2x2 matrices. We did that last time, and we'll use that complete theory to our advantage today. All right, so let's get cracking. Let's recap what we know about 2x2 matrices and get going with transformations of points on the plane. Back in a moment. Okay. Let me briefly review what we did in a previous lecture about 2x2 matrices, so they had a robust theory attached to them. So remember, a 2x2 matrix is just simply a matrix, an array of numbers with 2 rows and 2 columns. So here's one 2x2 matrix. I'll be generic, I'll just call it A, with entries A, B, C, D. Here's another 2x2 matrix, B, which will also be generic with entries E, F, G, H. Voila. And remember last time we did things like an arithmetic on matrices. We know how to add these 2 matrices. We know how to multiply these numbers by scalars, like I could do 2A would be just double all the entries within A, and so on. And we also learned how to multiply matrices if the numbers line up. And of course the numbers do line up because a 2x2 matrix and a 2x2 matrix are good. The right number of rows match the right number of columns, so you can do matrix multiplication within the square 2x2 matrices. Now recall, it worked as follows. It's a little bit tricky, but we use those path diagrams to motivate why people might want to do this very strange action. Here goes. So if I want to work out, say, A times B, what you do is you write the 2 matrices next to each other, C, D, and then, E, F, G, H. So there's the matrix A, there's the matrix B, and what we'll get, this is 2x2, this is 2x2, the 2's match in the middle, the result will be another 2x2 matrix, and we compute it as follows. For example, suppose I want this entry, the entry on row 1, column 2 of my answer. The idea is look at row 1 of the first matrix, look at column 2 of the second matrix and go multiply each item in turn. A times F, then go down, plus B times H, and that's it. There's only 2 entries in each row and each column. If I want, say, the first entry, first row, first column, go row 1, column 1, AE plus BG, AE plus BG, and so on. So that is very much a meaningful operation when you talk about like graphs of airline routes and so forth, as I did last time. It seems very strange, but it actually gives us a meaningful way to multiply matrices. Great. So we did that last time. We learned how to multiply matrices. Great. We also learned last time there's a very special matrix that acts like the number 1. It's called the identity matrix, which is 1, 0, 0, 1. And we showed last time if you take any matrix, maybe just A times the identity gets you back being to A. Or the other way around. Identity times A also gets you back to being A. So it's behaving like the number 1 in multiplication, because in ordinary arithmetic, 1 times a number is back to the number, or the number times 1 is back to the number. So it's behaving like the number 1 for matrices. And then we went further still, because then you wonder, okay, because in ordinary arithmetic, if I can multiply something to get 1, then that makes me think I can think of 1 over a number, do the reciprocal, or another word for reciprocal is inverse. So last time we talked about inverse matrices, which we noted as A minus 1. Now it's not clear when that exists, but if it does exist, we should have the property that A minus 1 times A gives you back to the number 1, well, matrix, identity matrix, and the other way around. A times the inverse should also get you back to the identity matrix. So if the inverse exists, you should have this nice property here. And then we even had a theory about when the inverses exist. So here's the matrix A. My board technique's getting strange. It turns out, and we proved this last time, that if you look at this thing called the determinant of A, which is A times D minus B times C, very strange number, where's that coming from? If this turns out to be not 0, then the inverse is sure to exist. The inverse is actually given by this formula. It's 1 over the determinant, 1 over AD minus BC, times this matrix. Turns out these two entries are switched, and these two entries are made negative. Whoops, make it look very neat. Whoa. So now you can see why you need this quantity to be not 0, so I'm going to do 1 over that number, it better not be 0, and if that number's not 0, then this turns out to be the perfect matrix that has this property with the number A. And one can check that by hand, it's true. Or you can derive it in general by looking at equations that arise from trying to get to what you want. In fact, we did that last time. So that was a very, very fast summary of the last lecture on matrices. If that was too fast, you might want to go back and look at that video there and the essay that goes with it. But this is going to be our leaping off point for today. So we're going to talk about 2 by 2 matrices and what they do to points on the plane. All right, so let me clean the board and then let's get cracking. Okay, now that we're done with our very speedy review of 2 by 2 matrices, that robust theory right there, let's now talk about how matrices can actually induce transformations of the plane. That is, I can use matrices to shift points around on the plane. Okay, how can I think of that? Let me do a specific example. Let's look at the matrix 2, 1, 3, negative 1. I just made up those numbers. So there's a 2 by 2 matrix. There's a point in the plane. Somehow I'm going to argue I could use that matrix to induce some sort of movement of that point in the plane. How's that possible? Well, it is possible. Think of it this way. You know, a point has some sort of coordinates. It has some x, y coordinates, so just x, comma, y. And then people notice, but look at that. I could think of that as its own little matrix. It's 1 row and 2 columns. It's a 1 by 2 matrix. And here's a 2 by 2 matrix. And we learned how to multiply matrices last time. So I can actually multiply this matrix and that matrix together. Now, I've got to be careful with the dimensions. I've got to make sure the number of entries in each row match the entries in each column. If you think about it for a little bit, you realize if I put the point x, y first and the matrix second, 2, 1, 3, negative 1, then the multiplications will work out. A 1 by 2 by 2 by 2 gives me another answer. In fact, let's do it. Let's do row 1, column 1. So I get 2 times x plus 3 times y. So 2x plus 3y. Then I'll get row 1, column 2, x take away 1, y, x minus y. Beautiful, beautiful. So now I've got another point. It's another 1 by 2. It's actually a point. So it did move the point. So hitting this point here, multiplying by this matrix, gave me a point somewhere like, 2x plus 3y, x minus y. So it actually moved it over yonder. The matrix, applying matrix multiplication to a point, thinking of it as a matrix, gives me a new point. Matrices do shift points around. Actually, they don't shift all the points around. For example, I do know, the origin 0, 0 won't be shifted. So every matrix will keep the origin in place. Because look, 0 times 2 plus 0 times 3, 0. 0 times 1 plus 0 times negative 1, 0. The origin stays the origin. Just like with the rotation, when I did that 90-degree rotation, that center, that origin stayed fixed, though other points can move. All right, so that's it. So a matrix does indeed give a way to shift points around on the plane, and they have to keep the origin fixed as well. All right, so now we have a way to use matrices to understand motions in geometry. Except there's one thing very annoying. Look here, I took the point P and I multiplied by the matrix A, and we got a new point over here, PA. People don't like that notation. In fact, people talk about these things called functions, some sort of operator, which they usually call F, and it operates on some quantity X. Now most people do numbers, we were doing points, but they've got something operating on something. The standard conventions become, over the centuries, always put the operator on the left and put the thing you're acting on the right, which is the opposite of what we've done. We've got the thing we're operating on, the point on the left, and the operator on the right. That's the wrong order. So people would prefer me to write the operator first and then what we're acting on second, A times P. But then there's a problem with that. A times P doesn't work. Let's do it. Here's A. It's 2, 1, 3, negative 1. Here's my point P as a matrix, x, y. Let me try to multiply it. They want the operator first, the thing acting on second, and I've got row 1, column 1, 2 times x plus, missing. 3 times y, and missing. It doesn't work out. It just doesn't work out. You can't do it. So, the logical thing that works for matrices doesn't fit with the notation that people want, which is annoying. But there is a way around this. There is one way around this. What people do is they say, okay, let's not change, if we want this notation to work, let's change how we write points. The problem is this is 1 by 2. They suggest do the following instead. Write it as a column vector. Let's now write points as column vectors, because then I could put my operator on the left, I could do the thing I'm operating on the right, and look, it will work. The matrix multiplication works. Row 1, column 1, I get 2x plus y, 2x plus y. Row 2, column 1, 3x minus y, 3x minus y. Wow. So if we write our points from now on as columns, as 2 by 1 matrices, then we can multiply on the left by a matrix. Now it's given me a different transformation though. It's not this transformation, look, the numbers are actually different. So I've switched things around. That's okay. We're still nonetheless getting some kind of transformation. So here's the game we're going to play. From now on, points, I know we write x comma y as a little 1 by 2 matrix, but when we work with matrices on points, the convention is please think of points as columns, as 2 by 1 matrices instead, and then multiply by matrices on the left. That's consistent with the notation people want. What can I say? It's just convention. And then we will get transformations that actually move points around on the plane, so we can start talking about geometry. Whoa, that was subtle, that was brain hurty, but there's the point. A 2 by 2 matrix does operate on points if you write them as columns, and you will get a new point written as a column. All right, so our game now is to actually start playing with some friendly transformations and see if they can be represented by matrices. And if I give you a matrix first, try to figure out what transformation it represents. It's actually kind of a fun game. So let's do that next. Okay, let's start with this example. Let's go with the identity matrix. What geometric transformation does that represent? That is, what does this matrix do to points on the plane? Well, let's find out. Here's a point. Let's call a general point. Now, I'm going to do it with algebra, with matrix algebra this time, so I'm going to represent my points as a column. Here's a point P, X, Y as a column. I'm wondering what the identity matrix does to a point. Well, let's work it out. I, operating on a point, would just be this matrix, 1, 0, 0, 1, operating on the matrix, on the column vector x, y. Work it out. Row 1, column 1, x times 1 plus 0 y's. X times 1 plus 0 y's is just x. 0 times x plus 1 times y. 0 plus y. Y. Oh! The identity matrix operating on a point gives you back the same point. It's not much of a transformation. It keeps the point the same. So when I take the matrix, the identity matrix on the plane, it moves this point here to itself. Keeps it where it is. It moves this point here to itself. Keeps it the same. Moves this point here and keeps it the same. So it's the transformation that does nothing. It just keeps everything where it is. All right, but that is an example of a geometric transformation, the one that does nothing to points. All right, that's our first example. Let's keep going. Okay, here's another 2 by 2 matrix. I've called it H. It's 1, 0, 0, negative 1. I've just changed the identity matrix a little bit. My question is, what does this matrix operation do to points in the plane? Well, let's find out. Let's take a general matrix H and see what it does to a point x, y. Remember, written as a column. So this is the matrix 1, 0, 0, negative 1 applied to the point x, y gives us a new point 1 times x plus 0 times y, x, 0 times x minus y, minus y. Okay, so it has changed the points. It has moved things around. All right, so there's the algebra. Now the question is, what is that geometrically? So let me draw a picture. Where can I draw my picture? Okay, I'm not very good with my board space here, but here's a point x, y. It has x coordinate x, namely, and has y coordinate y. This new point has the same x coordinate, but the y coordinate is now made negative, negative y. So it's still at the same x coordinate, but instead of being y up, is now y down. There's x negative y. Oh, it's taken this point and pushed it down there. In fact, it's just changing the y coordinate from positive to negative, or if I went the other way around, from negative to negative with negative y positive. It's actually a reflection about the horizontal axis. Oh, and that's why I called it H. This matrix actually reflects points horizontally about the x-axis, the horizontal axis. Great. Oh, think about it then. Here's a question. If I do one reflection about the horizontal axis, zoop, and followed by another reflection about the horizontal axis, zoop, then all the points should be back to where they started. That is, doing H and then doing H again should bring points back to where they started. Should have no effect on the points. Oh, the identity matrix doesn't move points. So I'm now wondering if H squared should be I. Doing H and then doing H again should not move points at all. In fact, that has to be true, and it'd be kind of fun. Check it. Take the matrix H, multiply by itself. Do you indeed get the identity matrix? Has to be true, but it'd be good to check the algebra. Great. Cool. We're on our way to seeing how matrices can be used to understand basic geometric motions, a reflection about the horizontal axis. This is good stuff. Okay, here's a question for you. Find a 2 by 2 matrix V, V for vertical, that corresponds to a reflection about the vertical axis. That is, all take a point x, y and move it to negative x, y. What 2 by 2 matrix has that geometric effect? Write one down. Okay, here's now a tricky question. I want to consider the reflection across a diagonal line, this northeast diagonal. So it takes an point x, y, and it will shift it to this point over here. Now, what are the coordinates of the image? I mean, obviously, this x coordinate here, if it gets flipped around the diagonal line, will become the y coordinate over here. So x coordinate becomes the y coordinate. And this y coordinate here, if it gets flipped around the diagonal, will become the x coordinate. So it looks like a reflection about the diagonal line just makes the x coordinate become the y coordinate become the x coordinate. That is, it just flips those two coordinates around, y, x. So there's the geometric effect of performing a reflection about the diagonal line. My question is, what matrix is that? So I'll call it D for diagonal, but I don't know what the matrix should be. A, B, C, D. Now let me give you a little piece of general advice here. Here's something that's a good rule of thumb. In fact, it's not just a rule of thumb, it actually speaks truth. So the thing to do is to look at very basic points in the plane and see what the matrix does to very fundamental points. For example, one very fundamental point is just go 1 unit along the x-axis, 1, 0. Another fundamental point to look at would be just 1 unit along the y-axis, 0, 1. And look what a matrix does to those two fundamental points. Now I'll keep it abstract for now. We're trying to work out what the diagonal matrix is, but I'll keep it like this. What does A, B, C, D do to the point 1, 0? Well, if I work it out, I get A times 1 times B times 0, so that's just A. C times 1 plus D times 0, C. That's just the first column. If I did A, C, B, D on the second fundamental point, 0, 1, I get 0 plus B times 1, B. 0 plus D times 1, D. That is the second column of my matrix. So I've just discovered something interesting. In general, I could look at a matrix and realize, oh, that is where the point 0, 1 moves. So 1, 0 moves here to AC. This column is where 1, 0 moves. Sorry, I keep saying backwards. 0, 1 moves. 0, 1 moves here. Interesting. So the columns of the matrix tell me where those two fundamental points move. So that gives me a technique to try to figure out what the matrix is for a given transformation. For the diagonal matrix, I want 1, 0 to move to 0, 1. Okay, I want it to be 0, 1. I want the point 0, 1, this other one, to move to diagonal reflection 1, 0. 1, 0. I can just write down where I want the two fundamental points to move and use them as columns. That's what this seems to be saying. That suggests D might be this matrix. Now we should check our work because that's just like a hunch. It was like really clever thinking here. Let's check. What does the matrix 0, 1, 1, 0 do at a general point x, y? I'll work it out and look what happens. 0, 1, y, y. 1x, 0, y, x. Yes, it did. It took a point, a general point, x, y, applied this matrix D to it, I get the point y, x. It did indeed switch the coordinates, that is, it really does correspond to a reflection about this diagonal line. Wow, did you get that? The first column of a matrix is where the point 1, 0 goes. The second column of a matrix is the point where 0, 1 goes. So if you've got a geometric transformation, think about where you want those points to go, and then you can probably just write down a matrix, and you should check yourself that it really is doing what you want it to do on general points. This is beautiful. All right, so that means I've got a challenge for you. Let me clean the board and show you my challenge to give to you now. Okay, here's my challenge for you. Write down a matrix for reflection across the other diagonal, the southeast diagonal line. And here's my advice. Figure out where you want the point, the basic fundamental point 1, 0 to go, and where you want the point 0, 1 to go. They will probably give you the columns of the matrix you're looking for, and then you can check it's doing the right thing. So can you write down the 2 by 2 matrix that does the trick here? Give it a try. Okay, well, one of the examples I started with, a matrix that does a 90-degree rotation. Can we figure out the 2 by 2 matrix that represents that particular geometric transformation? Why, sure we can. Let's do it. So here's a general point in the plane. If I want to rotate it 90 degrees counterclockwise, I want to take this here, I need to turn it 90 degrees and get this matching point at 90 degrees over here. Now, I need to figure out what are the coordinates of that. Let's see. All right, so it's taken this x coordinate and turns it 90 degrees, so that's now x high. And it's taken this y coordinate height and turned that 90 degrees, and it becomes over here, but in the negative side, negative y. I think I want negative y for the new coordinate here and height x all of a sudden. Is that right? Well, I don't know. Let's figure it out. I can do it as follows. All I need to do is look at where do the fundamental points go. 1, 0, and 0, 1. 1, 0 under rotation of 90 degrees, there it is, will go to 0, 1. Is that right? This point here, 90 degrees, up there. Where's the point 0, 1 go? Well, 90 degree rotation this direction gets me to negative 1. Negative 1, 0. Okay, so So that suggests the columns of the matrix I want are those, that the rotation matrix should be something like 0, 1 and negative 1, 0. All right, that's my theory for what the rotation matrix should be. Now, let me give myself a little bit of space. Let's check. Is it really doing the right thing on points? If I took this rotation matrix 0, negative 1, 1, 0 to a general point x, y, what do I get? 0, negative y, x, 0, x. I think my thinking, actually, though sketchy and quick as that was, actually turned out to be correct, because look at that, it's doing the right thing. It takes the point x, y to negative y, x. The rotation matrix of 90 degrees is given by that. Oh, a challenge for you. Write down the matrix that corresponds to not a counterclockwise, an anti-clockwise rotation. What matrix corresponds to a clockwise rotation of 90 degrees? Can you figure that out? Okay, let's carry on. Let's just go through more and more matrices, explaining more and more geometric transformations. Consider this matrix. I call it E sub k. So k is just some real number. It could be like 3 or half or 97 or square root of pi. Who knows? Just some real number. As the matrix goes k, 0, 0, k. So I'm wondering what the geometric effect is of this particular matrix. Well, if I just make it act on some points, I can actually work out the algebra of this. What does it do to a point x, comma, y? Well, it does this. Kx, 0y. So it's kx, 0x, ky, ky. Oh, what is that? What is that? So I've got a point xy in the plane. There's a point xy. Currently it's x units along the x-axis, y units along the y-axis. I get a new point that's now kx units on the x-axis, ky units on the y-axis. It's basically being pushed out by a factor of k. For example, if k was 2, I've doubled how far it is away horizontally, and I've doubled how far away it is vertically, which means I've kind of doubled how far away it is in general. It's pushed it away by a factor twice the distance from the origin. If this was 3, it would have pushed it away 3 times as far from the origin. If it was a factor of half, it would have actually shrunk it towards the origin by a factor half, by factor 2. All right. Oh, if k was 0, it would have squished everything down to 0. Like all the points go zoop. Like 0 is like a little, I don't know, sinkhole or something. If k was negative, then it's doing something really interesting. It takes a point over here and sort of like pushes it on the other side into the negatives, or vice versa. All right. People call this, now there's 2 words. Mathematicians tend to call this a dilation, though a lot of curriculum call this an enlargement. The word enlargement is a little bit scary because if k was a number that's like smaller than 1, a fraction between 0 and 1, it's actually shrinking things towards the origin. So it's not really enlarging, it's actually like shrinking. Oh well, but that's the word your curriculum uses, fine. Most people tend to call it a dilation, but you might be calling it an enlargement, but there it is. Lots of fun just playing with geometric transformations yet again. We've now got how to shrink things and move things and shrink things and enlarge things. Just awesome. Okay, a little practice question for you. Describe the geometric effect of this matrix, P, negative 1, 0, 0, negative 1. What's that doing to points in the plane? Okay, let's just do some more geometric transformations. Try this one. Consider the matrix SK. K is a real number given by 1, K, 0, 1. What's the geometric effect of that transformation? Well, one thing we do is just apply it to general points and see if we can recognize what's going on. So let's do it. Here's the matrix 1, K, 0, 1. Let's apply it to a general point x, y, and what comes out? All right, 1x plus ky. X plus ky. So the x coordinate has changed. We've changed the x coordinate. 0 x's plus 1y, y. The y coordinate hasn't changed. All right, so it's keeping all the points at the same height. So I've got some general point xy. It's going to keep the height the same. same y coordinate, but the x coordinates become x plus some extra stuff. And the extra stuff depends on how high it was. So I've got the same height, but a new x coordinate's over here somewhere. So it's shifting this point over yonder. In fact, if I had a higher point, a higher y value, then it's going to shift the point even further over. X plus k times y, where y is a bigger number. If I had an even higher point, y is even bigger number here, it's going to shift it even further over. It's sort of shifting things to the right, but it all depends on how high it is. Very hard to imagine what that is. But it's called a shear. People call this a shear of factor k. It's almost like slicing things, going, like pushing like a stack of cards, so you're like shearing the cards out that way. The high cards get pushed over more, the low cards get pushed over less. So there's a geometric transformation called a shear. In fact, let's do an example next, and hopefully maybe we get some more intuition about this thing with another example. Back in a moment. Okay, here's a scary looking question. Here's two triangles, triangle ABC on a graph, A primed, B primed, C primed on a graph. And the question is, find the matrix transformation that takes triangle ABC to triangle A primed, B primed, C primed. Whoa, okay, so I guess the question is assuming there is one that works. All right, so our question is to find it. All right. Let me just try it. If this method will not fail no matter what. I'm going to write down a general 2x2 matrix that's going to hopefully do the trick. But the thing is, I want to do what trick? What do I want it to do? I want to take the point, this point, A, 1, 1, and move it to A primed, which is what? 3, 1. So what a matrix come up with? It's got to transform that point that way. It's got to take the point 2, 1 and transform it over to what's that? 4, 1? And the third one it's got to do is take C, which is what, 3, 2, 3, 2, and take it over to 7, 2, 7, 2. So whatever matrix I write down, it has to somehow transform those 3 points that way. Okay, I'm going to try it out. Here goes. I'm going to do tedious algebra, and it won't fail. It just might be tedious. In fact, here it goes. General matrix A, B, C, D. I don't know what it's meant to be. 4 numbers, I'll do it. But I do know it has to take the point 1, 1 and get me 3, 1. So if I work it out, 1A, 1B, so it's A plus B, 1C, 1D, C plus D, and that's meant to be the point 3, 1. Oh, A plus B is meant to be 3, C plus D equals 1. I'm getting some equations that might tell me what A, B, C, and D have to be. The other one I have is A, B, C, D of 2, 1, which is 2A plus B, 2A plus B, 2C plus D, 2C plus D, and that's meant to be the point 4, 1. All right, I'll stop there for the moment, because that might be enough equations for me to work things out. Let's see, is it enough equations? Oh, I'm running out of space. All right, here goes, let's try it. So I want A plus B to be 3, so that tells me A plus B to be 3, B better be 3, oh no, I'll just write A plus B equals 3. Let's try that first. Let's not be clever before I do anything. C plus D is meant to be 1, so that has to be true. 2A plus B has to be 4. The reason I like that, 2A, A plus B has to be 4, and 2C, C plus D has to be 1. So I guess I am being clever after all, because look at this, A plus B is 3, A plus B is in there, A plus 3 has to be 4. I know right away that A better be 1. Woohoo! C plus D is 1, so C plus 1 has to equal 1. That tells me C better be 0. That's really sneaky. Here goes, what else can I do? Oh, if A plus B is 3 and A is 1, B better be 2. And if C plus D is 1 with C 0, D better be 1. All right, so my 4 equations did yield me 4 values A, B, C, and D, which means I should have the matrix that works. So it's telling me the matrix is, okay, let me erase all this. Sorry, messy board work. It should be A, 1, B, 2, C, 0, D, 1. And just to check myself, it should take the point 3, 2, I didn't use this one yet, to 7, 2. Does it take 3, 2 to 7, 2? Let's find out. 1 times 3 plus 2 times 2 is 7. 0 times 3 plus 1 times 2 is 2. Yes, it does. This is the matrix that does the tricks. In fact, that turns out to be a shear. It's of the form 1, something, 1, 0 and 1, and you can kind of see it did actually, like, if this was a deck of cards, it did sort of like smear the deck of cards out. Top cards moved further, though I guess the cards are like little different shapes at the top, and lower cards didn't move much to the right at all. It's a shear. So if you guessed it was a shear first, I guess another way you could have answered this question was, okay, let's do 1K01, check it was of that form, and then maybe do some work like this to see what K had to be, if you had that guess. All right, grand. If you didn't have that guess, just do A, B, C, D, and you could work your way through it. This is lovely stuff. So let's carry on. Here's a practice question for you. Matrix A is 0, 1, 1, 0. Matrix B is 0, negative 1, negative 1, 0. First question, what is the geometric effect of A? Second question, what's the geometric effect of B? And the third question is, what does BA, if I do those two matrices together, it gives another geometric effect, what does it actually do to this particular triangle shown? In fact, draw me the image of this triangle under BA. Can you do it? Can you think your way through that problem? Okay, so we've done some basic reflections, we've done some basic rotations, we've done some shears, we've done some enlargements and dilations and so forth, but we haven't talked about translations. So here's my practice problem for you. Find the matrix that translates all points of the plane just 2 units to the right. So every point just goes, shifts 2 units to the right. So that's a geometric transformation. So please find me the 2 by 2 matrix that gives that translation. Or explain why one doesn't exist, where you can't represent that as a 2 by 2 matrix. And actually, something I said earlier on in this video is a big clue to answering that question. Okay, a final practice problem for you to look at is this one. Here are 2 triangles, triangles A and triangle B, and I've given all the coordinates so you know what the corners are, what the coordinates of those points are. I'm wondering, is there a matrix that represents a transformation that turns triangle A into triangle B? Can you find a matrix representation of a transformation that turns A into B? Or maybe one doesn't exist. Now you know I'm tricky, so who knows? Can you find one? Can you not? Give it a try.